Okay, the next problem I want to look at is on page 427. We got example 4. We have a problem involving bearings. It tells us that the U.S. Coast Guard patrol boat leaves Port Cleveland and averages 35 knots, which is nautical miles per hour. And it says traveling for 2 hours on a course of 53 degrees. Okay. And then it says that, and then 3 hours on a course of 143 degrees. And we want to know what is the boat's bearing and distance from Port Cleveland. Okay. All right, so let's start out. We'll say that Port Cleveland is right there at the dot that I just drew. And it says that this boat travels on a course of 53 degrees. Okay. So keep in mind that the bearing, okay. The bearing here, if it's 53 degrees, I'm going to make my Port Cleveland here the origin, if you will. Remember, 53 degrees is 53 degrees from the north in the clockwise direction. So that means the boat's essentially going out like this, with that right there being my 53 degrees. Okay. All right. And then it says that after the 2 hours, okay, it goes on a course of 143 degrees. So that means we change direction. So 143 degrees, thinking about this right here being the north now, because this is kind of like our starting point now. So 143 degrees would be more than 90. 90 would be straight across at this point. Okay, so 143 degrees would be something like that. Okay, and then ultimately we're going to wind up at that point. Okay, so we're at a 53 degree bearing and then 143 degree bearing. Okay, keep in mind that it's 143 degrees with the north. That's what the bearing marks. Okay, so that's essentially our picture. All right. Now, with that said, the final answer that we're looking for is what's the bearing of our final destination, and also how far did it travel? Okay, how far did this boat travel? So let's talk about what we got going on right here. Okay, if I go from 53 in this direction to 143 in this direction, okay, what does this angle have to be? Think about that. What would that angle have to be right there? The angle of the turn, if you will. It'd have to be 90, wouldn't it? I'm going from a 53 to a 143. Okay. That angle right there would have to be 90, which is pretty convenient for us, isn't it? So that brings into play our trig functions. And then let's talk about angles here, or let's talk about side lengths here. The first one, we're going 35 knots for 2 hours. So that means that the side length of this one should be 35 times 2. So we're doing 35 nautical miles per hour for 2 hours. Okay, so that right there would be a 70. And then we're going 35 for 3 hours on this side. So 3 hours would make it go 105 knots, if you will. Okay. So the distance at that point from here to here would just be a Pythagorean theorem problem then, wouldn't it? If I know those two legs. So let's go ahead and do our Pythagorean theorem. 70 squared plus 105 squared. And then if we do square root of that, see if it's a whole number first. Turns out it's not. And they ultimately, though, in this case would accept a decimal answer here because we're talking about a distance. Should make sense. So with that said, we go 126.194 nautical miles. Okay. So that would be my distance from here to here, the length of that hypotenuse. Okay. All right. And then ultimately the question then, what about the bearing? Okay. So we want to know, we already know that the bearing is going to be from the north, so it's going to be 53 plus something. It's going to be plus this angle right here, okay, which we don't know. I'm going to call it x here in my drawing. But couldn't I set up a sentence that says tangent x equals 105 over 70? And that angle have to be in tangent with the opposite and the adjacent. And from there I could use my inverse tangent button. Find that angle. So if I go second tangent inverse, 105 divided by 70 gives me 56.310. I round to the nearest thousandth. Okay. And remember though that that angle is just from our triangle, so the actual bearing, okay, is that plus the 53. So if we add our 53 to that, we're going to have 109.310, and that would be the bearing for that particular trip. Fair enough? Questions? All right. There's one other type of problem I want to look at here. We're going to be asked to work with our problems for today, and that's dealing with what we call simple harmonic motion. If we have a point moving on a number line, we say it's in simple harmonic motion if its directed distance, if its directed distance d from the origin is given by either a sine or cosine function. Okay, the a and alpha, the amplitude and period numbers, are real numbers. Okay, and this w symbol here, which is another Greek letter, greater than 0. Okay, as long as that's greater than 0, the motion has a frequency of w over 2 pi, okay, which is the number of oscillations per time unit. Okay, notice it's really the same formula here for frequency as we had when we first talked about that, when we talked about the period of a sine or cosine function. Okay, but with that said, let's take a look at an example here. So if we have a mass oscillating up and down on the bottom of a spring, okay, so ultimately if we have a spring and the mass is going up and down, okay, its distance from the top of the spring is going to change. Okay, so we're making some pretty big assumptions here that we have perfect elasticity and there's no friction or air resistance. Okay, so ultimately it can be modeled by harmonic motion, and it says if the weight is displaced a maximum of 4 centimeters, and we want to find the modeling equation if it takes 3 seconds to complete one cycle. Okay, so keep in mind that we're going to write this in the form of y equals something sine of something t, if you will. So key issue here is can we find the amplitude and can we find the period? Okay. So let's take a look and see what we got here. So the assumption that you want to make, and this is what you want to do with any problem of this sort, is that we're going to assume that the spring is at the origin of our coordinate system, okay, times 0, and we're going to use the equation that a equals sine of, normally remember this is a b for us normally here, but they for this particular application they use the Greek letter instead. Okay, the maximum displacement is 4, and that means that the highest and lowest that we're going to go here is 4. That's going to be our amplitude, so recognize that as the amplitude. And it says that one cycle takes 3 seconds, okay, so the period then is 3. Okay, which means the frequency is 1/3, okay, which means that w over 2 pi is equal to 1/3. Okay, and ultimately that allows us to find this w, okay, which is the number that's going to go in front of t. Okay, so again, one cycle takes 3 seconds, okay, is the period, because how long the cycle takes is always going to be the period. Okay, the frequency, okay, we know is the reciprocal of the period. So the key issue is that if the period is 3, the frequency is 1/3. And as stated on the previous slide, okay, that w value is the number that we're looking for here, and we know that the frequency is w over 2 pi. So if we set that equal to 1/3 and use the cross product property, we'll have 3w equals 2 pi, and then w would equal 2 pi over 3 if we divide. And ultimately that's the number that's going to go here, which is going to represent why our period is actually 3. Thinking about it backwards also is if that's our b value right there, okay, all right, and I want to know what my period was, okay, I would go 2 pi over b, wouldn't I? Just like normal. And if I do that, 2 pi over that, that'd be the same as multiplying 3 over 2 pi, and I would ultimately get my answer for the period being 3, wouldn't I? Okay. So really, is that process any different than what we've been doing in terms of finding the period? Well, if we know the period is 3, okay, then we can use our 2 pi over b formula as well. Okay. So that's really not different than what we did in our previous problems. Okay. All right, questions so far?